Good afternoon to all. Welcome to this third session, doubt clearing session of the course Engineering Thermodynamics. So I'll now take up the first question for today. So it is, as per our generic list, it is question number 59. Okay. So the question is, you told an example of water in a long cylinder in yesterday's and today's lecture and told it to be in static equilibrium. Was it in thermodynamic equilibrium also? Okay, so let me take up this question. So the answer is, if it is in thermal equilibrium and also it is in chemical equilibrium, because mechanically already it is in equilibrium, then obviously it will be possessing thermodynamic equilibrium. Okay, so let me once again little bit elaborate on this. So what I have done, I have taken a container and inside this container I have now filled water. Okay, now this water column, as we know that at different locations it is having different pressure, and that pressure is almost linearly varying. That we have seen why it varies linearly in our morning session also. Okay, now the idea is, as per the definition of mechanical equilibrium, a system will be in thermodynamic equilibrium if and only if pressure everywhere is same. Okay, so this condition is applicable when we are not considering the effect of elevation. Okay, so it means if pressure everywhere is same, we will not be having any bulk motion of the fluid within the system. Now, when we consider the situation of elevation also into consideration, then obviously pressure everywhere will not be same. Rather, we will be finding that as depth will be increasing, we will be having more pressure. Okay. So why that happens, that if we consider the elevation and if we consider fluid to be in static equilibrium, though we are having variation of pressure, still we are having the mechanical equilibrium established. So the reason is that if we take, once again, I'll now go to the previous explanation only. If I take the water column, so this water column is having certain weight. Okay, so that weight of water column is actually supported by this pressure which is acting. Now, if I take somewhere the section of water column only up to some intermediate height, so at that particular section, what will be happening? Whatever the pressure required to support the liquid column, that will be only till that weight, whatever we will be considering, that weight mg will be less actually. And if I take it at the mid plane, then weight will be mg by 2. Okay, so because of that, whatever the variation we are having in the pressure along the elevation, that variation is actually due to the static equilibrium only, because if we are having more depth, then we have to provide more pressure in order to support the weight of the liquid. Okay, now if we take that this liquid is nothing but water, then obviously we know that water is a homogeneous substance. Okay, so that's why it will not be having any other chemical affinity to react, so it will be in chemical equilibrium. And if we consider this water is at ambient temperature, T ambient is the temperature of water, it means it will not exchange any heat with the surrounding, and everywhere within the water column temperature is same, then it will be in thermal equilibrium, and finally we can say it is in thermodynamic equilibrium. Am I correct? Is it clear?
So now we can define state to it.
Yes, we can define. Yeah.
Thank you.
Okay, the next question is, can you explain specific volume and graph related to it once again? So this question is from Akash. Akash, have you seen my previous doubt clearing session? Akash is here. Anyone else is also having same doubt?
Sir, only about the graph.
Okay, okay. So I tried to discuss this question in my previous session also. Let me once again explain it. So the idea was that if I take del V by del M along ordinate, and if I take delta V along abscissa. Okay, so we are saying that we are having certain critical limit of delta V dash above which we are having constant volume of specific, constant value of specific volume, and below this we are having actually fluctuation. So why fluctuation is there? Let me just explain it. So in reality, what will be happening if I have, say, a container, and inside this container some gas is filled. Now let us consider these black circles are nothing but the molecules of the gas which I have filled. Okay. Now what will be happening if I consider that my limit delta V is tending to 0. So it means whatever the elemental volume I am tending to specify, the value of specific volume, that is nothing but a point. Okay. So now it may happen that sometimes I am pointing to a situation which is basically is nothing but in some void space. Okay. So if our limit is pointing to a void volume, in that case what will be happening? We will be having delta V by delta M. Now for this particular void, delta M will be 0. If delta M is 0, then obviously this value will be approaching to infinity. Okay. And now let us consider another situation that I am pointing on the nucleus of an molecule. So if I am at the nucleus of an molecule, so we consider that whole mass is concentrated at its center only. Okay. So in that case, what will be happening? My delta V by delta M, if I see, the value of delta M will be some finite mass. Okay. And delta V is already very small, which is pointing to 0. So that's why we'll be finding our value of specific volume as very small, which will be tending to 0. Okay. So because of that, when our delta V is actually tending to 0, either we may end up in getting infinite value of specific volume, or we may end up in getting at some location some very small value of the specific volume. Okay. Now if in place of delta V tending to 0, if I consider delta V approaching to delta V dash, and this delta V dash I specify some critical value above which, critical value of the control volume above which our assumption of continuum is valid. In that case, what will be happening? When I will be pointing, say, some volume, say this is one of my volume, delta V dash, say another, this is my another volume, delta V dash. So roughly, if I consider that my system is homogeneous, roughly I will be finding that within this delta V dash, I will be having almost same amount of matter. Okay, the mass of the matter will remain almost same in that delta V dash, because our assumption of continuum is valid and matter everywhere is almost homogeneous. Okay, so that's why beyond this value of delta V dash, we will be finding a constant value of specific volume, and before that we will be having nothing but oscillating values in between infinity and a very small value. Now is this point clear?
So we are
Yes,
approaching
sir.
this limit from right hand side or left hand side?
We are, see, the only thing what we are doing, the only idea of specifying this limit is we are pointing to a small element. That's it. We are not going into mathematical details whether we are approaching from left side or approaching from right side, but the idea is we are pointing to a small value. Okay, elemental volume.
Okay, sir.
Sir,
Yeah, please.
as far as we consider this diagram and this graph, so
Yeah.
in simple words, if we just talk of physical significance of this graph, so
Yes.
can we simply say in very simple words that as gradually we proceeded to increase our system under consideration, this delta V, okay,
Yes.
so as our delta V became large, as our system under consideration
Yes.
from the whole container, as our system from the consideration became larger and larger, our system started becoming continuum system.
Yes, that's correct.
From,
Exactly correct.
if we have a container and
Yeah.
And if in the same container at a very small observatory system, we have a non-continuum system, and
Yes.
at a certain point, the same container will become continuum.
Yes, yes, if it is large.
Yes, if it is large enough. If it is delta v dash, if it is around delta v dash, so
Yes.
at any particular finite value, it will become continuum.
Continuum. Yes, correct. Exactly correct.
Okay, sir. Thank you, sir.
Okay, so then should I go with next question?
Yes, sir.
Yes,
Okay.
sir.
Next question is, please elaborate pressure gauge once again with the graph, last slide of today's lecture. Okay, so today's lecture last slide was pressure gauge. I didn't get your question. Is it was it about pressure gauge or it was about temperature measurement?
Sir, we were discussing temperature scale at the end.
Yes.
sir. Temperature scale.
Yuvraj, are you connected? So Yuvraj has asked this question. Please elaborate on pressure gauge once again. So pressure gauge is nothing but, let me briefly tell. So probably I might have specified, now I could recall, I might have specified that I'll be having a control volume, a fixed volume, and inside this fixed volume, I will be having some gaseous medium, okay, some gas, and this entire thing be putting inside the medium where I want to basically measure the temperature. And once we are having the equilibrium, actually thermal equilibrium, then we will be measuring the pressure of this gas. Okay, so for measuring the pressure of the gas, yes, now I could recall that I have shown that we will be using a dial gauge. Okay, so we will be using a dial gauge for measuring the pressure of this gas container. Okay, so this dial gauge, basically we use Bourdon type pressure gauge. So probably this is beyond the scope of this particular course, so that's why I'll not discuss it over here. Okay, for more details you can refer to Bourdon type pressure gauge, those whoever is actually interested in knowing more details. Okay, so this is nothing but pressure measurement device. So measurement of pressure is easy, so that's why this particular device is used over here. So this is a commonly used. Many times if you see your laboratory setups, you will be finding some scale printed on some circular sheet, and then you are having some needle, and then that needle basically points to some value on the scale and specifies the value of pressure. So that particular thing is actually known as pressure gauge, not dial gauge, rather we call it as pressure gauge. Okay, am I clear? So I thought that this could be the question. So probably if Yuvraj is here, you can clarify. Others can also just let me know whether I am clear whatever I have explained.
Sir, can you explain once again?
Oh, okay, so what I told, the idea is we are having a fixed volume. Inside this fixed volume, we have some gas. Now, because we have seen that temperature is nothing but equal to A plus B into P. So it means if we know the value of these coefficients A and B, and if we know the value of pressure, we can determine the value of temperature. So obviously for coefficients, how to determine, I have already told you that we will be actually taking two known points, T1, P1 and T2, P2, and then we will be substituting these points into our governing equation, and we will be finding the value of coefficients A and B. Now once A and B are known for any specific gas which is inside this fixed volume, after that we can employ this device for measurement of the unknown temperature by just noting the value of pressure. Okay, so for example, initially this gas was at some ambient temperature, T ambient, and now we have placed this in some hot medium. Okay, so if medium is hot, obviously the temperature of this medium will be greater than temperature of the ambient. So now what will be happening, this hot medium will be transferring some heat to this gas. Because of that, the pressure of the gas will be increasing. Now that pressure of the gas actually we are measuring with the help of pressure gauge. And the pressure gauge which is employed over here, it is Bourdon type pressure gauge. Okay. Am I clear now?
Yes, sir. Thank you, sir.
So,
Yeah, please.
so in the equation that you just wrote, T is equal to A plus BP, did we
Yeah.
get that equation from the pressure gauge, from the system that we drew?
Yeah, so what we have done, I have already told you in the morning, what we are doing basically, we have taken the ideal gas assumption, okay, that our gas inside is nothing but ideal because we are operating this gas volume at low pressures. That is first assumption. Second thing we have considered that this container, whatever we have considered, it is of fixed volume. Okay, so that's why whatever gas we have filled, its amount will not be changing, its volume will not be changing. So we know as per ideal gas equation, PV is equal to mRT. So for some specific type of gas, R will be constant, mass is fixed, M is constant, volume is fixed. So pressure is nothing but directly proportional to temperature. So that's why we are fitting temperature linearly with the pressure. Now is it clear?
Yes, sir.
So why the constant
Excuse me,
A is
sir?
coming in this equation?
Why
It
the
should be like Q is
constant?
equals to lambda times P.
Because
No
we are not,
constant should be there.
because we don't know about the absolute scale of the temperature. Like for absolute vacuum where we are having no matter, at that point it means the idea is at pressure P equal to 0, if T is also 0, then obviously there will not be any intercept A. But we are not sure that at absolute vacuum we will be having temperature value also 0. Okay, because majority of the temperature scales which are designed, these are nothing but on the assumption of some reference fluid states. Okay.
So, sir, this means this equation isn't for the absolute scale. This is valid if we are using Celsius scale or Fahrenheit scale.
No, so that is what I think you have missed some points from my morning's lecture. I told you that when we have fitted this scale on this temperature versus pressure plot, okay, so when we have extrapolated this line, we found that this line, so let us consider it is meeting on this point. I have drawn actually more on the, okay, let me draw another line. So let us consider that this dashed portion is nothing but extrapolated portion. Okay. So I have told that when pressure is becoming 0, corresponding to that in degrees Celsius, whatever the value of temperature we are getting, that is minus 273.15 degrees Celsius. Okay. And if we see in Kelvin scale, as this value is nothing but corresponding to 0 Kelvin, therefore Kelvin scale is my absolute temperature scale. Okay.
Okay, sir.
Temperatures.
Yeah, please. Is this
You are
one
getting
clear?
T1 and T2.
Sorry,
Hello?
why? Yeah, please.
How you are getting T1 and T2?
Okay. So what we are doing, we are converting, say I have a piston, this one cylinder, I have a piston, okay, and over this piston I have say some weight W, and say this W weight is such that it is maintaining atmospheric pressure inside the cylinder, and inside this I have first this cylinder entirely filled with water. Okay, say at ambient temperature 25 degrees Celsius. Now what I'll do, I'll heat this water. So when I'll be heating, what will be happening? Can you answer what will be happening?
Temperature will rise.
Temperature will rise and the system will slightly
And volume will increase.
increase. Yes, system will slightly try to expand because we are maintaining constant weight. Okay, so pressure will remain constant. And finally we will be finding a situation where our system has entirely reached the value of temperature 100 degrees Celsius. Okay. After that point, what will be happening within our system now? After that point, now inside our system, we will be finding that volume will change significantly. Okay. Volume will change significantly. It will increase significantly, and all the liquid will now change into vapor phase. Okay, so all the liquid will be changing into which phase? Vapor phase. So that at what point this will happen? This will happen at boiling point.
When temperature reaches 100 degrees Celsius.
Yes, so from there we can say that from the physical state of the system, we can say temperature is 100 degrees Celsius. Similarly, at ice point, we can say temperature is nothing but our 0 degrees Celsius. Is it clear?
Sir.
Yes, sir.
Okay, so should I move to next question?
Yes, sir.
Next question is, please explain quasi-equilibrium and non-quasi-equilibrium process. Oh, so you are forecasting what we will be studying in the next lecture. So probably this I will be completing in our next lecture. Okay, so whatever the lecture we will be taking on Monday, there I will be discussing about this question only. Okay, so now I am skipping this from here.
Okay, sir.
You are forecasting what we will be studying in the next lecture. Please once again explain last slide containing T equal to Vp. Is it clear now, Bharat? Majority of the things I have discussed.
Yes, sir. It is clear now.
Okay. Then which measurement of pressure is correct? Manometer measurement or barometer? Both give same value. There is no difference between manometer and barometer. Manometer will be giving us manometer mainly employed for measuring the pressure difference. For example, if we connect two different unknown pressure sources across the two tubes of the manometer, so we will be knowing the value of pressure difference, and barometer is mainly employed for measuring the pressure of ambient. Okay, and both the measurement methods are based on same principle, so that's why both are actually having same accuracy level. Is it okay?
Yes, sir.
Today you told us an example of two copper blocks and you said resistance varies with temperature. At high temperature block had low resistance, and as no, I think I told opposite, no?
Yes, sir. Yes, sir.
No, sir.
I told opposite. So whatever you have written, Asutosh,
Yes, sir.
I told
No,
just
sir. Sir, you told the same that I have written.
what I told.
Sir, the block at higher temperature had lower resistance than the block at colder temperature. You said this.
But sir,
Okay.
it should be opposite.
Okay.
Yes,
Okay.
sir.
Okay. So probably I don't know, because we are not stopping in between continuously. We are speaking, so somehow I missed then this point, I think. Then next question is, could you please explain P observe vacuum equal to P atmospheric minus P gas? Okay, in vacuum P is 0. So how this equation is possible? Okay, so I think she's who has asked this question? Dikshika. So I think you have confused in between the absolute vacuum and vacuum. When we are having absolute vacuum, then only we say pressure is 0, and vacuum we say when we are having pressure less than atmospheric pressure. So is it okay now, or do I need to explain?
Yes, sir. It's clear.
It's
Thank
clear.
you.
Okay. Then next question is, can you please explain why density of manometric fluid is taken to be much greater than the density of the gas? Okay, so that is first part. So normally what we want to do, we want to have density difference. We want to have immiscible liquids. Now, in this particular situation, density was greater. If density is not greater, in that case, what will be happening? Let me explain with the physical situation. Let us consider we are having a pipeline and flow is happening through this pipe, and in this pipe we are having some obstruction. So we have some obstruction over here. Okay. Now let us consider rho W is the density of the fluid. So water is flowing inside this pipe. Now what will be happening? We have made few pressure tappings. So I have made 2 pressure tappings, one at the upstream of the obstruction and another at the downstream of the obstruction. Okay. So now what will be happening if I want to measure the pressure drop because of this obstruction? Okay. So what will be happening? We all know from our basic understanding of fluid mechanics that we will be having something like this. So if you apply the continuity, if you apply your energy equation, you will be finding here velocity head will be very high. So because of that, pressure head will be low at section 2 and at section 1 pressure head will be larger. Okay, so P1 will be greater in comparison to P2. This point is clear? Whatever
Yes,
I have
sir.
drawn, is this clear?
Yes, sir.
Okay. Now, what I am doing, I am taking some manometric fluid inside this pipe. So, if my pressure over here is more, towards which side we will be having more height?
So the other side.
The right hand side. Okay. So, it will be like this. Now, whatever the magnitude of P1 minus P2 we are having, corresponding to that, we will be finding, if I consider this as H, I will be having nothing but equal to P1 minus P2 equal to, if I take density of manometric fluid as rho m. So I will be having rho m into GH minus rho water into GH. Is this point clear?
So
Because
rho W.
yeah, rho W is nothing but the density of water. Okay. So in this particular case, what we are having, rho m is manometric fluid density and rho W is water density. So rho m is greater than rho W. Okay. If rho m is lighter than rho W, because of that, what will be happening? This lighter fluid now will try to rise because of the buoyancy effect, and this will not stay in the U bend portion of the manometric tube. Is this point clear?
Yes, sir.
Okay, so we require heavy fluid which is staying in the U bend portion. When we take inverted U tube manometer, so we may have configuration where this U tube is actually oriented in the upward direction. So this type of manometric configuration is known as inverted U tube. So when we use this configuration, then we use manometric fluid of lighter density than our working medium. Okay.
Yes, sir.
Sir,
Yeah, please.
sir, in the manometer figure that you drawn morning,
Yeah.
the rho m is greater than rho of gas.
Yes.
But you consider the height to be same.
Yes.
Is it necessary because rho m is maybe greater, but rho g still be considered if the h is different?
No, generally when we fix the manometer, we try to keep the height of both the tubes identical. So because of that, what will be happening? Whatever the rise we will be having in one side, same fall we will be having in the other side. So for example, you can see my present situation. Here I have actually written rho m minus rho w into GH. When we are having the density is comparable. When density will be negligible, then I can neglect that. Okay.
So height needs to be same on both sides.
Means if it is not same, then obviously you have to do the additional measurement. Apart from reading the level of the manometric fluid, you have to read the level of the other fluid also. Okay. So that will be like more complex system. So that's why the general trend is that we try to go for devising a manometer which is having almost same height.
Okay, sir. Thank you.
Okay, the next question is Okay, now next question is, can you explain the negative gauge? So negative gauge is clear now?
So can you explain with the graph? The graph part I was unable to understand.
Okay, let me explain once again. And third is, and your third part also you have asked. So ideal gas thermometer is clear now or not?
Yes, sir, that part is clear.
Okay, so I'll now explain only the graph. Okay, so particularly I'll now plot graph only for the negative side. So what I am saying that I have pressure over here, and this bottom line is corresponding to absolute vacuum, where we are having zero pressure. Then we have some line over here which is equal to 1 atm, and this pressure is nothing but 101.325 kilopascals if I take scale of pressure in kilopascal. So any pressure which is below my atmospheric pressure, that either we call as negative pressure or we call as vacuum pressure. Okay. And when we measure the value of pressure with reference to absolute, then that will be actually my absolute value only, but this absolute, as it is less than atmospheric, so I'll be calling it as vacuum. Okay. And if I measure the same value with reference to the atmospheric, so with reference to atmospheric, it will be nothing but negative, and whatever the value I'll be getting, that will be my gauge pressure, but this gauge is also in vacuum. Okay. And this is my P atmospheric. So that's why we say that P absolute means absolute pressure in vacuum is nothing but equal to atmospheric pressure minus, so this atmospheric also I am writing in absolute, means with reference to 0, what is the value of atmospheric pressure? Okay. If with gauge I write, then it will be 0 only. Okay. So P atmospheric minus P gauge in vacuum. Is this point clear now?
Yes, sir.
Sir,
Yeah, please.
sir, is it possible to have a gas with less than 1 atm pressure?
Yeah, we may have gas with less than 1 atm pressure, that we can do with the help of some external mechanical power we need to employ to make that system below atmospheric. Okay, so it is very difficult to perfectly achieve the absolute vacuum, but somehow close to 0.3 times of atmospheric pressure is actually achieved with the help of some forced mechanical arrangement.
So whatever is less than 1 atm, we will call it vacuum.
Yeah, we call it vacuum, and absolute vacuum we call when we are having zero pressure.
Zero. Okay. Okay, sir.
Okay, then next question is why there is a need to define gauge pressure even if it is not possible, even if it is not the actual pressure. So the need for gauge pressure is because when we will be using a device, any device, so obviously we will not be having anything available with perfect vacuum. Okay, so that device will be always open to ambient pressure only. So with ambient pressure, we specify the value of that device as equal to 0, and then whatever change we measure, that we try to measure with reference to the ambient pressure. So that's why normally there is requirement of this gauge. Is this point clear?
Yes, sir.
Okay, then next is barometer used only for measurement? Yes, whatever the ambient you are having, because there you are having some open tank like structure. So in that open tank only this atmospheric pressure will be acting. So that's why it is particularly called as barometer. If we are using it for any other purpose, then normally we go for the manometer.
Sir?
Yeah, please.
So in the morning you told the size of the barometer does not matter as long as it is not of capillary dimension.
So I was telling that dimension of the tube, yes.
So does shape matters or not?
Shape is also not much, not of much importance, because what we are doing, we are measuring the pressure, and pressure is a parameter which is only changing with the elevation. Okay, so irrespective of the shape of the container, it will be giving us value.
But sir, in the questions that were asked in JEE Advanced, there was a question in which there was a conical shape barometer, and it
Okay.
shows different measurement because of the some curvature problem.
Yes, so curvature problem will be coming into picture when you are actually considering the effect of surface tension. Okay, so normally we try to go for the smaller tubes. So in case of smaller tube, what happens if we go for circular profile, we will be having actually uniform curvature everywhere. So that will be like coming into picture if your capillary effect is also prominent. Okay.
So we ignore meniscus here.
Yes.
Okay, sir. Thank you.
Then next question is, please, which question I have to take now? I think I have to take 71 number question. Yeah. So can you explain last part in the lecture when you calculated temperature using pressure and extrapolating the graph? I am confused with, is it now clear? Question number 71 already I discussed. Vikas, is it clear?
Yes, sir. Sir, it is clear.
Okay. Is the copper block example? So probably I think this resistance, I mentioned it wrongly. So this you can now correct it. Okay.
Yes, sir, it's clear.
Then we define continuum by homogeneity. So we talk of homogeneity in accordance with properties like temperature, etc. Also, or we just see the particles are dispersed No, we normally talk in terms of the properties only. Okay, because it is very difficult to observe the motion of the particles. Is it clear, Kusagra?
Sir,
Yeah, please.
if we talk about the homogeneity, suppose on the basis of temperature.
Yes.
So yesterday you said that continuum and thermodynamic equilibrium system are two different things. They are not the same. But if we define continuum on the basis of that the temperature everywhere in every section of the container is same, the similar way we define the thermodynamically
No.
system
See,
also.
the idea is not that. So probably you are taking it wrong. What I am saying, if the temperature continuum, so just let me illustrate with the help of an example. What I am trying to say, probably you are confusing. Okay. So let me take this as my container, and inside this, if I have gas, some gas, say air, I have air here. So as a whole, if Knudsen number, or I should say L for this system is very large in comparison to delta, I can say that within this system, everywhere I have actually continuum. Okay, so our medium everywhere is nothing but homogeneous. But homogeneity in the medium doesn't reflect that we will be having same value of the property. Now in this container, let us consider that if I am adding heat from the downside. So from here I am adding certain amount of heat. So because of that heat, what will be happening? The portion which is in the immediate vicinity to the surface, that will be having high temperature, and as we will be moving away from this heated surface, gradually our temperature will be decreasing. While this process is happening in the transient state. Once it has reached the steady state, then obviously everywhere temperature will try to get almost the same value. But still, if we are adding heat and from the top we are rejecting heat, then we will be having across this entire span of the medium, we will be having gradient of temperature, okay, through which heat will be actually flowing. However, everywhere we are having continuum, whereas the properties are not same. Okay, so this process is not in thermodynamic equilibrium, but it is a process, it is a system having continuum. Is it correct?
Yes, sir. Yes, sir. Yes, sir.
Okay, then next question is it possible to have gas less than 1 atm? I think already I have cleared this point.
Yes, sir. Yes, sir.
Please explain ideal gas thermometer again. So is it now clear, or do I need to explain once again?
Sir, can you explain it again?
Okay.
Can you explain it again?
Okay. Okay. what I am saying, that we are considering a container, and this container is of fixed volume. Okay, and here inside this we have certain gaseous medium. Now, if we consider that this gas we are taking at very low pressures, okay, so under this condition of low pressure, this gaseous medium will be behaving as ideal gas. Okay, now if this is ideal gas, then I can write down the equation PV equal to mRT. Now for this particular gas, R will be constant. Now whatever the medium I have taken, that is inside a fixed volume, so M will also be constant, and volume already we are having a fixed boundary container, so this is also a constant. Okay, so it means in this particular situation we are having pressure and temperature as directly proportional to each other. Now we have come up with the idea that we already are having devices available for measurement of the pressure. Okay, so it means indirectly if we measure the pressure, we will be able to determine the corresponding value of the temperature, the corresponding change in the temperature. Okay, because if we are changing the temperature, pressure of the gas will also be changing in the same proportion under the assumptions what we have considered. Okay, so because of that, now we will be employing some system over here in order to measure the pressure of the container, and we will be immersing this entire container in our medium where we want to measure the temperature. So obviously if the medium temperature is different than the temperature of the gas, there will be some heat transfer, and once this heat transfer has taken place and both the temperature of the gas and temperature of the medium has reached identical, at that point we will measure the value of the pressure. Okay, by just noting that value of pressure, we can say that how much change in the pressure has happened from our initial state, and corresponding to that we can measure how much change of temperature has happened. Okay, so that's why we have related this temperature with pressure in the form of linear equation A plus BP, and then we have used some known conditions in order to find out the coefficients A and B. Okay, and once this equation is known, then by just knowing the value of pressure we can find out temperature. Is it clear now?
Yes, sir, it is clear.
Okay, so probably we are now done with the questions. Is there any other question?
So there's one question about from I think yesterday's lesson.
Yeah, please continue.
So it's about the difference between state and properties, because the term were used quite often, and I was unable to differentiate them.
So state and property is almost similar. So state is something which represents the thermodynamic equilibrium physical condition of a system. Okay, and anything which characterizes that physical state of the system is called as property of the system. Is
So
it
that means when the system is at thermodynamic equilibrium, we call it its state, and the properties that define, like the temperature or pressure, that are its properties.
properties? Yes.
Okay, sir. Thank you.
Sir, you told during state's definition that it is a point where the substance is not changing.
Yes, so it means it is not changing. It means it is in the stage of thermodynamic equilibrium.
So not changing.
Not changing its physical state.
So we can call it a phase in which it remains in a single phase.
No. For example, let me give you another thing. Okay. Let me illustrate with the help of an example. Say I have a container. Inside this container, I have, say, some liquid water, and amount is ml, and above this we have some vapor of water only, and it is in phase equilibrium with liquid phase. Okay, and say mass of vapor is mv. So what is happening at this point? Mass of liquid and vapor are not changing with each other. So it means their physical state of the system is not changing. So whatever the bulk properties this system will be occupying, these will be remaining constant. So I can call this as in some state of thermodynamic equilibrium. Now, are you able to relate the difference between state and phase?
Yes, sir.
Can you again explain chemical equilibrium?
Okay, chemical equilibrium is a very, very simple thing. Okay, for example, if you are having methane, if you are having propane, if you are having butane and air, all the mixture of different gases is contained inside a container. Okay, and now the temperature of the container is also such that temperature of this entire mixture is such that they can actually start the ignition process. Okay, so it means whatever the different components or different phases we are having in our system, all are having at that particular point chemical affinity to react. Okay, so if they are having chemical potential or chemical affinity to undergo through a chemical reaction, so it means these are not in chemical equilibrium. On the other hand, if we consider, say I have helium, I have argon, okay, like all the inert gases, mixture of the inert gases, and these are once again put inside a container. We know that all these inert gases are nothing but non-reacting, so these will be having zero chemical potential to react with each other. So we can say that these are nothing but in the, because their chemical composition is not changing. Okay, so we can say these are nothing but in the chemical equilibrium.
Oh, thank you, sir.
Sir,
Sir, do we have to learn the definitions of these things, or is it just for understanding?
It is all for understanding. Now probably I'll try to give you one first assignment over this weekend. So you'll be finding your majority of the assignments actually will be analytical only, where you have to do a lot of problems. Okay. So once we are continuing our discussion beyond first law of thermodynamics, you will be finding our entire subject will become completely numerical. Okay.
Okay, thank you, sir.
Sir, is
Sir.
resistance directly proportional to temperature or inversely?
Resistance, basically what will be happening, if you are having high temperature, then you will be having more resistance, so it will be directly proportional. Okay, am I clear now?
Yes, sir. Sir, will you be giving the assignments for this weekend?
Probably over this weekend I'll give. No, you need not to do it over the weekend only. You will be having some time of 3 to 4 days to submit that. Okay, I'll be posting over the weekend.
Okay, sir. Thank you.
Individual or group activity?
Sir.
Individual. What is the group activity in subject? You are not doing any project, na? So it is your individual learning process. Okay.
So when will we have the quiz for this?
I'll be announcing at least 1 week before. Okay.
Okay.
Yeah, please.
Length.
Have you seen my
Yes.
first doubt clearing session?
Yeah.
Oh, you are having general query why we are using length scale. Yeah, the idea is okay. The idea is basically you just think something that you are studying a system at the molecular level. Okay, means you are consider yourself you are having something which is in the length scale of nanometers. So what will be happening at the nanometers? Will you be so at the nanometers, what will be happening? You will be able to see the location of individual molecules or not? Asutosh?
Yes, sir.
Yeah, at the what I am saying, at the nanometric level, you will be able to see the this one individual behavior of the molecules. Okay, so because of that, what will be happening? You have to, while you have to define some characteristic of the system, you have to consider that effect of, you have to taken into account the effect of individual molecular motions. One more easy example could be, for example, if you take a piece of pipe, okay, and inside that piece of pipe, if you put 2-3, say some particles of sand, okay, now what will be happening? If you just vibrate that piece of pipe, so because of that, what will be happening? You will be having some movements within these particles.
Yeah.
You will be having some movement between the sand particles. You are having only 2 to 3 sand particles, so that movement will not be able to sufficient to define the overall vibration behavior of your entire pipe piece, okay, pipe section, whatever you have taken. Now, in another situation, what you do, you take the same pipe piece and you try to put significant packing of the sand particles inside that one, okay. So now, first thing is that your sand particles movements will be restricted, and at the same point of time, whatever the vibrations you will be subjecting to your pipe, almost same vibrating behavior will be shown by your sand particles. Is it correct or not?
Sir.
So that is the idea actually. It is something that whether we are having uniformity within our medium or not. Okay. And another point is, if we relate this vibrating example only, say initially you are giving vibration of simple harmonic type nature, and here you are having time period of 5 seconds. So when you are having less particle, there are chances that some of the particles will be striking to the surface of the wall, and they will be completing their this complete vibration cycle even before the span of 5 seconds. Whereas if you are having closely packed particles, they will be trying to follow the same time scale as that of the your object, whatever you have taken. So are you trying to relate slightly?
Yes, sir. And
So the
what
idea,
is the characteristic length?
characteristic length is something, for example, if you are having pipe, okay, so flow is happening through a pipe, so we can consider diameter of the pipe as our characteristic length scale, okay. On the other hand, if you say you are having a combustion chamber inside this one, your IC engine, okay, so whatever the size of that combustion chamber is there your all the gases will be filled, so that size of the representative, so characteristic length is nothing but a representative dimension of the size of the thermodynamic system.
Sir,
Yes, sir.
resistance is directly proportional to temperature, but in yesterday class, sir, you write it reverse. In
So
example.
in the morning lecture, probably I have done mistake in writing the resistance. Okay, so I have written it wrongly, I think.
Thank you, sir.
Okay, so do you have any other doubt clearing session for today?
Yes, sir.
Yes, sir.
Okay. So at what time it is starting?
3 o'clock.
Okay, so then I am actually closing this session. Okay, so you all can leave.
Thank you, sir.
Thank you, sir.
Thank you, sir.
So there's one thing I wanted to ask.